Next, we consider Lorentz boost in Minkowski space. Unlike the Euclidean space whose length is defined according to Pythagoras' theorem, we have point x1, x2, x3, y1, y2, y3. What is the distance between the 2 points? High school students may know. X3, y3 squared. That's fine. However, in the Minkowski space that is different from Euclidean space. Euclidean space is only for the spatial part of the word. Before Einstein, they didn't think the time is correlated with the space. But after Einstein, time is correlated with space, and this was wrong because we have two different units, two different physical dimensions. After multiplying by speed of light, that is invariant. Speed of light is invariant. So after being multiplied by the speed of light, it has the equivalent dimension as the length, and then that's not the end of the story. Rotation gives x squared in the Euclidean space invariant. That's the reason why any point on a sphere in the three-dimensional Euclidean space, x squared equals r squared. That's fine. However, in the Minkowski space that we are living in is not a picture fixed at time t. We have time and space. They are correlated but consistently. And how? That is ct squared subtracted by spatial distance squared equals c tau squared, and both of them are invariant. In rotation, only x squared r squared is invariant. However, if x carries a velocity, something is moving with the velocity, then time is not an invariant quantity anymore. For a moving object, time flows very slowly. And the scaling factor is gamma, and that gamma is called the Lorentz factor. And that Lorentz factor is determined by the velocity of a particle, like that. The ratio of the speed of an object with respect to the speed of light that is invariant. And the resultant relative motion is called boost. Suppose that you are standing in here, you have a watch. Your hand and watch, they are stick together. This watch does not move at all. This one shows tau, that is called proper time. However, we have a ball, flying ball, with velocity v, and there is a watch attached to this ball, and you watch this watch, moving watch. This one shows T. And T is gamma tau. This tau, this T, they are different. T is always greater than tau. That is called the proper time. Okay? That's the fact. Details are already discussed in the Y series. I don't want to repeat that. So, what we need to do is find out a boost matrix that is very similar to cosine sine minus sine cosine for the rotation matrix. This one after the rotation, x1, x2, this guy after the rotation, invariant. Sum of square is invariant on the rotation. However, our constraint of relativity, that is for the Minkowski four-dimensional space, this is a three-dimension and this additional time dimension. These four-dimensional Minkowski space, what is invariant? Ct squared subtracted by x squared is invariant. Okay, so this and this, they are quite different, but you remember e to the x, e to the ix, they are correlated with analytic continuation. This exponential function and this is oscillating function, cosine plus I sine. But if you know what about what e to the x is, you can multiply I to this argument to find the structure of cosine and sine. Very strange, but this happens. So from this, we can guess what the structure of this boost matrix is. Let's see. First of all, this is called the square. In Euclidean space, we have inserted identity matrix to define the distance square. In Minkowski space of four-dimensional space-time structure, we need metric tensor to define the scalar product. We insert negative sign on the spatial part. So this is different. 1, 1, 1 for the three-dimensional Euclidean space is inserted between two vectors to define the A dot B. But in here, in Minkowski space, zeroth component represents the speed of light multiplied by time, subtracted by spatial vector square. Okay, let's see. Just assume this is the boost matrix. Let's see what's happening inside. You multiply this four vector. This is called the four vector. It's not stating four vectors. It is a four hyphen vector because it is a vector that has four components. That's the reason why we say four vector. Four vector is to be multiplied to this boost matrix. This one gives this gamma A0, gamma beta A1, beta gamma A0, gamma A1, and these perpendicular direction y and z directions are transverse direction invariant. only the longitudinal direction, longitudinal, that is a x direction is a parallel to velocity. So we say it is a longitudinal. Only the longitudinal and time interfere together. Let's see. If you square this, a0 prime squared, a1 prime squared, and so on, a0 squared minus a1 squared, a2 squared minus a3 squared. This should be invariant. Then we will find that gamma squared subtracted by beta gamma squared equals 1. It requires. What's that? We can factorize this gamma squared and 1 minus beta squared. By the way, gamma is defined by 1 minus beta squared. If I substitute them, this is nothing but 1. Haha. If I work on a right triangle with A, B, and C, A squared plus B squared equals C squared. That's fine. So because of that, divide both sides by C squared, I would obtain cosine squared plus sine squared theta equals 1. However, what I have right now is not the sum, but the difference. In this case, very simple. To replace sine, cosine to cosine hyperbolic, sine to sine hyperbolic. This is called analytic continuation. You remember exponential function is 1 plus x squared, and so on. Sine x, 3 factorial x cubed, and so on. Cosine 1 minus or x squared, something like that. This one selects the even terms and odd terms. Okay? Exponential consists of even contribution called cosine and sine. But if I want to express this one, I don't have flipping sign plus minus in here. Simple separation of even and odd part is cosine hyperbolic and sine hyperbolic. Let's see. Just same exponential, but positive, negative. So this is a usual way of separating a function into even and odd contribution. F of x, even part is sum of f of x plus f minus x. F of x, odd part is 1/2 f of x minus f of minus x. So even part of the exponential function is cosine hyperbolic, and odd side is a 1, 3, 5. This is sine hyperbolic of x. If I make use of these, instead of having cosine squared theta plus sine squared theta equals 1, we have cosine hyperbolic squared phi subtracted by sine hyperbolic squared phi equals 1. This is identical to what we have right now. Minkowski space structure has this kind of form. So this booster matrix is parameterized into this form: cosine hyperbolic, sine hyperbolic, sine hyperbolic, cosine hyperbolic. It is opposite to, in comparison with the usual rotation matrix, cosine theta, sine theta, minus sine theta, cosine theta. different structure is it anti-symmetric or the off-diagonal piece? So symmetric. They are different. Next, gamma equals cosine hyperbolic, and gamma beta equals the sine hyperbolic. And if you take the ratio, you usually cosine theta, sine theta over cosine theta is called tangent theta. What I need to do is gamma beta divided by gamma. If I want to find the relative velocity itself, it's good to take the ratio of sine hyperbolic to cosine hyperbolic. So it is sine hyperbolic phi divided by cosine hyperbolic phi. Okay. Similarly to the rotation, we'd like to see what the inverse matrix for the boost transformation is. The answer is put the negative sign on it. Is it true? Let's multiply this guy to here, cos sin sin minus. If I had cosine square theta minus sine square theta, it's wrong. It is cosine 2 theta. What's that? This is a hyperbole. Hyperbole. It is just one. It's not cosine sine like this. It's not cosine. It's a hyperbolic. Hyperbolic. Then it is just one. The same is true for all the diagonal components at 1. Then means if I substitute parameter minus phi, it is inverse. Okay, so we will continue to study this with this what we have obtained until now for the future, for the repeated boost. For example, if you drive a car, a very long car, and your friend is driving a car on your car, on top of your car, and another guy drive a car on top of it too, and so on. In Galilean relativity, you will reach this original velocity is v, then you can add up all of the velocity to reach your velocity to reach infinity. But that is not true in Einstein's relativity. Any object cannot fly faster than the speed of light. We will see in the next class.